Hey guys, this is for checkpoint 1.16 from the text for our AB, our Calculus AB content. We're talking about the fundamental theorem of calculus, and this is specifically part 1. In this problem, one thing that we want to tie together, and the reason for fundamental theorem of calculus part 1 existing, is that if we have a function and it's defined to be the area under the curve, because you allow your boundaries to change, you actually get an area that can be described in terms of how far along on the function's x-axis are you, and at that certain value, calculate your area. Change your x-coordinate, you change your area. So there's a relationship based upon where you stop on the x-axis and the area under the curve for that function. Therefore, the antiderivative is also a function of x. Now, in that relationship, what happens if you take the derivative of the area, meaning the derivative of the antiderivative? That should cancel out. We'll see some weird situations. This might come up in one of the standards that you're working on, but I'm going to answer specifically this question. One thing I also did here is I graphed it. So I've got the square root of x squared plus 4, and it's because I'm seeing this integral occur from 0 to r. I just want to kind of show you that r can be at any of these points right here. Let me go like this. X equals r. Let me go x equals 0 r. Yeah, that'll work. And then I'm going to go a times. And so I want a slider for r, and I want to make the a go away. It's a little Desmos magic for you. So if you imagine the area under the curve being this section, as r changes and moves forward, this area continues to add up. Move r just a delta x over a tiny amount, you get a slightly bigger area. The thing is, when you look at the limit as that delta x approaches 0, this whole derivative conversation, what ends up happening is that the derivative of g, it'll be with respect to r, because that's the variable that's of focus, dg dr. We wind up actually having this function. Remember, if we evaluate it with 0, we're going to get a constant, but we're evaluating it with r. So we have the antiderivative of this function. Take its, that would be like how do I say this in the right way? I want to use capital letters. I'm a little bit shook that we're not using capital letters for the antiderivative, but it would be the antiderivative of this function, then we'll take the derivative of it. So maybe I'll reference it like this. D of, we should at some point know how to do this, but we're not ready for that yet. So I'm just going to use g, which represents the antiderivative of x. And then it's with respect to r. Oh, my bad. It shouldn't be an x here. It should be an r, because that's our upper limit of integration. And then when you take the derivative of the antiderivative, you wind up with the, what do they call it? It's the integrand of the function, which would be square root r squared plus 4. The 0 results in a constant, and the derivative of a constant is 0. So we would, tack on a plus 0, a minus 0. It doesn't really change anything. This is our antiderivative, our derivative of the antiderivative. Thank you, Fundamental Theorem of Calculus Part 1. What? See you in the next video.